We saw these images on the last slide. We see water, ammonia, graphite, ionic and covalent bonds. I guess those are not well. I guess they are molecules, but they're showing covalent bonds between chlorine atoms and sodium and chlorine ions. Then we see sodium chloride, sulfate, and adenine. But all of these look different, don't they? Not only because water and ammonia are very different substances, but because these are different models. Models are models are ways to represent specific things about a phenomenon. In this case, we see a different model on each picture. And each model has certain advantages and certain disadvantages. None of them are perfect representations of reality. They all emphasize certain qualities that we want to study. For example, in this is called the space filling model of that we see in the water molecule. And this particular space filling model shows us the sizes of the atoms. And we can see here that the atoms have different sizes. The red atom is oxygen, the blue atoms are hydrogen. And we can see that the oxygen atom is significantly bigger than the hydrogen atoms. And we can also see that the hydrogen atoms are positively charged and the oxygen atom is negatively charged. The reason is because the electrons are more attracted to the oxygen than they are to the hydrogen. If you had chemistry, you may have learned the term electronegativity. So we would say that oxygen is more electronegative than hydrogen, and that's why the electrons are more attracted to the oxygen side of water than to the hydrogen side of water. We also see that atoms can join together, they can combine at certain angles. So if we look at the second and third images, ammonia and graphite, we see that the atoms are bonded in to form certain specific shapes. You have a pyramid shape with the ammonia, and you have from graphite, you have sort of a star-looking shape. But those shapes form because the angles bonded between the atoms are very specific. Now, the ammonia, the model that's used for ammonia, shows the shapes of the atoms in a different way, and so does the model for graphite. Some atoms will form repeating geometric structures. These are called crystals. So graphite and sodium chloride both form crystals, and you can see that they are in very specific repeating structures. And you've seen crystals before, and each substance forms its own shape of crystal. So you can see that the sodium chloride crystal is kind of a cube shape, and the graphite crystal is sort of a star shape. And these shapes are repeated throughout the crystal, no matter how big the crystal gets. We have two main kinds of bonds that we tend to focus on. We have covalent bonds and ionic bonds. In a covalent bond, the atoms that are bonded together share pairs of electrons in these merged clouds. In an ionic bond, what happens is one of the atoms takes an electron from the other atom. So then, in this case, in the image here, the chlorine atom has taken an electron from the sodium atom. So the chlorine atom now has a negative charge. The sodium atom has a positive charge. And as we have learned, oppositely charged particles attract. So the chlorine and sodium atom are attracted to each other, and that's why they form the shape we see for the sodium chloride crystal. The image shown for sulfate is called a Lewis dot structure. This model emphasizes the electrons that are free to form bonds. So each of these dots represents an electron that may be able to form a bond. Not all of them are, but if you understand Lewis dot structures, then you're able to see all of the outermost electrons, and those are the ones that can possibly form bonds. Lastly, we see this is a model that's often used for organic substances. And in this kind of model, the lines represent pairs of shared electrons in covalent bonds. So where we see one line, then that each one line represents two electrons. So we see the electrons that are forming the bonds here, which is different than the Lewis structure, where we see the electrons that might be available to form more bonds.